So what is up, everybody? This is the first video of how to graph series for J mains and advanced. Basically, I would like to share my knowledge on graphs through the series. And the first thing we'll be discussing in this video is what functions are. So function is basically a mathematical equation, I guess you could say. Something of the form y is equal to something. Anything of the form y equals some function of x. And basically what f of x even means is that you put a value of x into the function and it gives you a specific output, right? For example, if I had to, let's take y is equal to 4x. If you put x as 1, you get the output as 4. So essentially how I like to think of a function is that it's a sort of machine. Okay, so this is like a sort of machine, and imagine like a conveyor belt. Okay, this is like a conveyor belt. So over here, you put in, let's say, something like a tree. So if you were to put a tree inside, what does the machine do? It gives you like a sort of output, maybe like a chair. It takes the tree and converts it into something that you want to use, probably. Same thing. If you extrapolate the same logic, what a function is that if you put something like 1 as your number, it gives you another number like 4. This is what happened in this case when x, you put it as 1. This is a very simple function, but functions can be anything. So let us discuss the different types of functions. So you have algebraic functions. There are 3 types: polynomial, rational, and piecewise. So I'll be discussing how polynomials, rational, and piecewise functions work using Desmos, but this is just for visual understanding right now. Polynomial functions can look anything like this. They're always smooth. That's one thing you have to remember. Polynomial functions are always smooth. And you have transcendental functions. Basically, these are... hold on. In transcendental functions, you have trigonometric, which are, you have your sine and cos, and you have your tan x, probably. You have tan x, something like that. How I like to remember transcendental functions is that they transcend all limits. So for example, sine x, it is periodic from minus infinity to plus infinity. And you have tan x, which basically transcends the limit of infinity. So at pi by 2, it's tending towards infinity. And similarly, you have even your secant x. All of these have something to do with infinity. And exponential and logarithmic. If you see exponential functions, they're either always increasing or always decreasing. So there's, of course, exponential growth, right? Even these functions tend to go towards infinity. So it just keeps increasing. And similarly, logarithmic functions look somewhat like this. And even they have something to do with infinity, basically. So in e power x, which is this graph, after x equals 0, which is this part, it just keeps increasing towards infinity. But if you see x lesser than 0, which is this part, it is always decreasing. Infinite decay, basically. So these are the broad classifications of functions. And let us actually see how they work using Desmos now. So let's start out with polynomial functions. The definition of polynomial function is anything of the form y is equal to x power n. And here, n can be any number greater than... It should be positive and greater than 0. So how that works is, right now, if you put x equals 0, then you have y is equal to x power 0, and anything power 0 is just equivalent to 1. So this gives you a constant function. So this is essentially what it gave you, right? So, and the next most basic polynomial function is y is equal to x. Here x is just 1, so y is equal to x. And as you can see, this is a straight line. And this is perfectly symmetrical across this half and this half. And why that's important is that all inverse functions are symmetrical about this line. For example, if I were to take sine x and arc sine x, arc sine is basically sine inverse. If you were to zoom in on only this part, you can see that these both are symmetrical across this line. So this is probably the most important part of y is equal to sine x. Other than this, you have very little to know about this. And basically all straight lines are a modification of this y is equal to x. If I were to add a constant like plus phi, what I have is the previous graph, but every point on this is just shifted by phi units. I can do the same thing with the negative sign, and it's all shifted down by phi units. And right now, y is equal to x is the same as y is equal to 1x. And 1 is the same as tan 45. I mean, it's probably not good to write 45, instead pi by 4. So what pi by 4 is basically the angle that this makes with the positive x-axis. I can change this to anything and get a different value of slope. I can change this to pi by 6 and I have a slope of 1 by root 3. So basically any constant that you insert before your x just modifies the slope. So let us just add a parameter like b, or I think you're comfortable with m probably. Y is equal to mx. So as I vary m, you see how the slope changes, right? And I can even change by adding another parameter like mx plus c, I can make every possible line that maths has to offer. For example, I can make a line that passes through this point. So take up a challenge, make a line pass through the point 20, 0. So right now I've inserted a point 20, 0. And by just modifying these two parameters m and c, I can make it such that it passes through the point. See, so basically I have modified it in such a way that it passes through this point. And same thing, I can just put really any point. Even, okay, let's take negative 5, 4. So let us make it pass through this. So, okay, let us make it have a positive slope and I'll make it pass through this. So as you can see, these are the only two things you need to get every point in space. There's another way of writing the same line equation, which is y minus a is equal to m into x minus b. So if you're confused as to why I've written it in this way, I want you to imagine this as a variation of y is equal to mx. If this is y is equal to mx, I want you to lift this graph. I want you to lift this graph and overlay it on this line. So if I were to just substitute point, okay, I think it's better to make this a and this b. And if I were to call my minus phi as a, I had to just put minus of minus phi. And if 4 is equal to b, guess what? That exact same line is you just lift it and place it over this point. So this form of a line is also very important. Essentially, you want to replace your x minus a is the point a comma 0 and y minus b is your point 0 comma b. Okay, so I can, a better demonstration would be this. So by varying a comma b, I'm making this line pass exactly through this point. And it's actually very important that you learn how to parameterize your maths. That's how you understand it the best. Always bring in variables like parameters like b, a, m, n, etc. So that concludes your straight line. And if you were to put n is equal to 2, let's just put n equals 2. And what this basically gives you is a parabola. Y equals x square. So this is essentially what it's giving you. The same logic of shifting origin works even over here. Let me take a random point a comma b. So let's make it really random. Okay, so that's a pretty random point. So how do I lift this parabola I have over here, and place it over here? In order to do so, what I would do is just replace x with this bracket version of x. And all you have to do is subtract this with your point a. And you really need to understand the logic behind this. So basically, okay, let's finish this and then I'll explain why that works. Why this shifts the graph. So this is what we had initially. If you go to 0, comma 0 and insert 0 and 0 over here, what you have is y is equal to 0 and y is also 0 at this point. So you have 0 is equal to 0, which is a true statement. So what you want to replicate over here is also a true statement. What values of a and b do I give for it to become a true statement? So the most obvious thing is, let us first try to make x equal to 0. So if you want to make x equal to 0 at this point, so if you want to make x equal to 0 at this point, the x coordinate of this is currently minus 10, right? So basically I want to subtract this value. So I have to, in order to make minus 10 equal to 0, I have to add a 10. So that is why essentially this becomes y is equal to x plus 10. And another way of writing plus 10 is minus of minus 10, right? So what I've essentially done is just subtracted the x coordinate. And by doing so, I have kind of shifted it by this much. And now I want to shift it by the y coordinate also. So I would just have to subtract the y coordinate, which in this case is minus 9.7, which is just point B. So in general, if you want to shift any equation to a specific point, then just replace x with x minus a and y with y minus b. This works with every function. And then this is with only these two coordinates, you can get most of the quadratic equations. But if you wanted to change the width of the parabola, you could modify this parameter m. So anything positive value of m kind of shrink the parabola, while negative values of course invert the parabola, and values very close to 0 make it extremely broad. This is a very good way of understanding what a parabola is, but there's another very important way of writing parabolas, which is what you would have learned in 10th standard and in other classes. Y is equal to ax square plus bx plus c. I'm pretty sure everyone has come across this also. And just to show you how even this is a completely valid form of writing a parabola, you can just modify any of these three parameters and get every type of parabola in existence. For example, I want to make a parabola that passes through, let's take 5, 4. I will modify only these three parameters and make it pass through this. In most of the cases, you would have a is equal to 1. In most of the cases, a is equal to 1. So I'll keep a is equal to 1, and I will just modify, let us keep b is equal to minus 1. And just by modifying c, I'll try making it pass through this point. Let's take minus 20. And there's a point, yes, exactly this point, where it passes through the point 5, 4. And this concludes what a parabola is. And now by changing x is 3, what you essentially get is a cubic polynomial. In polynomials, cubic polynomials basically defined by the general equation y is equal to x cube plus anything of lower powers, x square plus x plus a constant, like let's take 5. So cubic polynomial can be followed by any polynomial which has a degree lower than 3, and it will still remain a cubic polynomial. And the same logic applies even over here. If I wanted to make this y is equal to x cube pass through the same point 5, 4, what I would do is I would replace this with a bracket and just subtract it by the coordinate I'm looking. So right now the x coordinate is 5, so let's just put 5 over here, and the y coordinate is 4. I can replace y with y minus 4, and essentially the polynomial which previously looked like this now passes through this point. And this sums up all polynomials. You can extend it to power n is equal to 4, n is equal to 5, and so on. And now the question that people usually wonder is, what if I put n is equal to minus 1? This time you get something that is also smooth. This is also a smooth function. But why is this not considered? a polynomial is because it is not continuous. It is not differentiable at 0. So if you notice, this goes towards minus infinity, and suddenly pops up at plus infinity. So there is a discontinuity over here. And polynomials are basically recognized by the property that they're continuous everywhere. So that is why we call any function with a power less than 0, like -1, -2, etc., are called rational functions. And if I put -2, you get a function similar to this. It's very important that you know how to graph each one of these. I advise you to open Desmos on your own and understand why certain graphs look like the way they are. For example, if you want to know why it goes towards infinity near 0, is you just have to understand why. When you put power of -2, what you're basically doing is doing power x square, 1 over x square. And let us take an example of 0.5. And essentially, when I have 1 divided by 0.5 is basically 1 by 2. And if I were to square this, right, basically this is equal to 1 divided by 1 by 4, which is equal to 4. So essentially, as I make this smaller and smaller, the number I get just becomes bigger and bigger. So that is why you get this huge upward spike as you tend to 0. And if I want to understand why it tends towards 0 as I'm increasing the number, then let's take up the same example. Let's take a big number like 9. So 1 over 9 square is essentially just 1 over 81. And 1 over 81 is a really small number. I'm guessing it's somewhere like 0.0125. Because I know 1 by 8 is 0.125. So 1 by 81 should be similar to 0.0125. And let's just verify. At 0, at 9 it's 0.123, which is pretty close. So as you keep increasing, this just dies. So by understanding graphs like this, by analyzing their behavior before 1 and after 1, and before a critical point, basically over here 1 can be seen as a critical point, -1 and 1. So anything that is before -1 is an infinite decay, while anything after -1 and before 0 is like an infinite increase. And similarly over here, this is anything before -1 is an infinite decay, which is extremely rapid. And anything over here is also like infinite decay. But this one is not as spiky as this. It doesn't. So this one's super spiky. So the advantage of learning graphs in this way is that you can graph pretty much things intuitively. For example, if I were to graph x square plus 1, let's say you didn't know how this graph looked like. How would I graph this immediately using intuition? First, let me just, so y is equal to this. So let me take a point where x is equal to 0. If I put x is equal to 0 in this equation, I get y is equal to 1. So the graph looks like that. And then let us take another value of x. Let's take x is equal to 1. I get y is equal to 1/2. And similarly, if I were to take another point, let's say 2. Over here I get 1 divided by 5. 1 by 5. Right. So I have 3 points. And this basically gives me the general trend of how the graph should look like. I would just start off by connecting these points, and I already understand that as I increase the value of x, like if I were to take something like 10, I already get something like 1 divided by 101, which is extremely small. So I wouldn't even bother to graph it, and I can already extrapolate the graph as something like this and just tends towards 0. And if you have the question, why have I not considered negative values? The thing is, if you see x square, just remember this x square is an even function. What an even function basically is that it is symmetrical across the y-axis. For example, y is equal to x square. It looks like the mirror image of this side over here, right? So whatever happens at the right will automatically just happen even at the left. So if there is a point called 1 comma minus half, like 1 comma half, then there's going to be a point called minus 1 comma half over here. Similarly, there's a point 2 comma 0.2. There's going to be a point minus 2 comma 0.2. So that is how you get a graph like this. And you can mess around more just by changing. Let's say I wanted the same graph, but I wanted it to pass through 2 comma 0 and follow the same trend of like decay, over like a really gradual decay, but it needs to pass through 0 comma 2. So then what I would do is I'll just change the constant, and it follows the same idea. And you can do this for any constant, like 10 makes it passes through 10. And what if you wanted to change how broad this graph is? Right now this looks a little bit sharp. What if I wanted to broaden this so that it at least passes through these 2 points over here, this point over here and this point over here? I would just change the constant before x. So let's just call this m, and I will vary m such that it passes through those 2 points. Maybe I think 0.05. Okay, 0.04. Yeah, 0.04. So by changing the value of m, I'm able to make it broaden or less broaden. And it's really fascinating to see how a negative value of m makes the graph discontinuous. I would like you guys to kind of reason this to yourself as to why it becomes so discontinuous. That's your homework for today. So I think today we have basically discussed polynomial functions and rational functions. And probably next video we'll be discussing transcendental, logarithmic, piecewise, and all of those. So take care and see you next video.